Welcome to the Internet Ecosystem and Evolution course. My name is Gábor Rétveri and I'm going to be your lecturer for the first couple of lectures in this course. As you might already be aware of, the Internet Ecosystem course is an advanced master's level networking course on the very deeply technical parts of the workings of the internet, and as such, there is quite a bit of a background that we assume that you're already aware of, mostly related to TCP/IP protocol suite and layer network protocols, and so these basics of networking you will need to know in order to be able to progress to the rest of the much more technical parts of the lecture series. As it turns out, many of you come from different universities, different backgrounds, and you have different education, and it turns out that many of you, or some of you actually miss some important knowledge to be able to understand what's coming. So in this first lecture we are going to give you a short introduction to TCP/IP and the workings of the TCP/IP protocol suite, and the rest of the lectures will build on the knowledge that we acquire here. So we are going to very quickly jump through all the necessary basic information about network communications and telecommunications, but we won't have time to actually delve into the very details. So everything you hear during this lecture, we assume that you already know this background, and please, if you just watch these videos and take a look at the slides, please, if there is anything you don't understand, anything that you see is that was missing from your previous educations, then please take this as an indication that you have some work to do before progressing to the rest of the lectures. Please make a Google search, read Wikipedia, and try to come to terms with these basic definitions, because we won't be able to go and we'll be able to jump to the rest of the lecture without you understanding at least the basics of TCP/IP. So this is going to be a lecture on the basics of internet protocols, TCP/IP, layer network protocols, and then we are going to start from the bottom of the protocol stack, from the link layer, and build all the way up to the transport layer. Again, most of the things that we are discussing are just the high-level ideas. About the rest of the details, please consult your favorite textbook on network communications. Okay, so what actually network layers are? The internet is a surprisingly complex system. We are just most of the time we just take the internet for granted. We just switch one of our end hosts on and then connect to the internet, and we assume that the network will transmit all our packets from sources to the destination, as it usually does. Turns out that this couldn't be further from the truth. One of the main objectives or the main goals of this lecture series is to make you aware of that this is a very, very complex, very large scale network, and you cannot just take it for granted, because the underlying machinery and underlying mechanisms are in one hand very complex, and on the other hand fairly fragile. But theoretically we assume that the internet makes network communications available to the communicating parties in a global scope, so everything from intelligent IoT coffee machines to supercomputers and iPhones, whatever you switch and connect to the internet, these things will theoretically be able to talk to each other and exchange network packets. again, theoretically, every country to every other country, let's say just more or less, because there are of course exceptions. You won't be able to send packets from Palestine to Israel or from Israel to Iran. And one of the good examples is, for instance, the Great Firewall of China, which pretty much makes it impossible to send arbitrary content into mainland China. But theoretically, we assume that every two nodes can communicate, or every two end hosts can communicate without boundaries through the internet. Of course, politics, security, and business interests sometimes override this idea, or this ideal state of the art. Now, for any two of these diverse devices to be able to talk to each other, from coffee machines to supercomputers, to be able to exchange communications in a reliable and dependable way, we need a fairly complex machinery and mechanisms to be in place. These are called the standard network protocols, and the network protocol stack is this collection of functionalities that we need all the hosts that are connected to the internet to implement for them to be able to speak to other hosts. So theoretically, we have end hosts, A and B, talking to each other, and of course there are routers on the internet that make it possible for these two hosts to exchange packets. But if we just deconstruct this very high level view and take the data flow, then we are going to see that the picture is a little bit much more complex than that. In fact, the entities that talk to each other through the internet are applications. So one application talking to the other, an internet or a web browser talking to a web server, a mail client talking to a mail server, a DNS client sending a query to a DNS server, etc., etc. These are applications that run on different computers. Now the internet and basically all protocol stacks are based on this idea that these processes perceive as if they talk to each other. So and protocol can or any application talking to another application believing that the actual peer is the other application, but it turns out that the flow of data between these two applications is much more complex than that. In fact, when the application sends data to the other application, this basically just goes through this fairly complex path through the internet. It goes through the transport protocol layer, the internet layer, and the link layer, and then it goes to a first hop router. Here is the first hop router, which basically just processes the packets all the way up until the internet layer, and then through the progressing through all these different link and internet layers, the packet arrives, or the data actually arrives to the end host, and the end host process the data up from the link layer all the way to the application layer. So in order for this whole machinery to be able to make this impression to applications that they are talking to each other, we need a fairly complex set of functionalities. This is the idea of the network stack that produces or that implements all this functionality, and the protocol layer in this protocol stack is a simple module of this suite, which is responsible for a well-defined subset of the protocol stack's functionality. Okay, so every entity in this diagram, in this data flow, just have the impression that they are talking to directly to the other peer, but in fact the communications happens through the mediation of all these different protocols in the protocol stack. The TCP/IP protocol suite is modeled somewhat vaguely on the open systems interconnection model. If you are as older as me, you must have learned the open systems interconnection model as this ideal a splitting of a network stack into this ideal set of network protocols, of these protocol modules. And this is International Standard Organization protocol or definition. And in these standards, the network stack consists of 7 layers. But in fact, the internet just simplified quite this 7-layer network stack into just 4 layers: the link layer, the network layer, the transport layer, and the application layer. So at the link layer, we see those basic functionalities that make it possible for two hosts directly connected to one another via an internet cable or Ethernet cable or an Ethernet switch network to talk to each other. If you know PPP or ADSL, good for you. If not, these are not really important any day, at this point. The network layer makes it possible to connect these different Ethernet islands or local area networks into a global network. So this is the networking layer where we find IP, the Internet Protocol, ICMP, ARP, DHCP, and some of these functionalities that makes it possible to just connect all these diverse and heterogeneous local networks into a global network. On top of the network stack, there is the transport stack. Now, this is the stack that makes it possible for any two applications on any two end hosts on the internet to directly talk to each other through a reliable communications channel or an unreliable one, if we are talking about UDP. And on top of the transport layer, we see the application layer protocol. HTTP and HTTPS are good friends to all of us. These are the protocols that operate the World Wide Web. DNS, SSH, all these protocols, you name them, these are all application layer protocols which work on top of the transport layer protocol functionalities and make it possible for the corresponding applications to exchange data. The very idea how this works is the concept of encapsulation and decapsulation. So the big idea here is that whenever an application just wants to send data, so one application tries to send data to the other application, remember that it has this impression that these two applications, these upper layer entities, talk directly to each other. It just takes the data that it wants to send to the other application and adds a header, which is basically just a set of metadata to this data unit. These are the upper layer headers. So if you are talking about, for instance, HTTP, the message will be, please give me this and that URL or this and that HTML page. And the actual header will be the HTTP header, which will identify the HTTP protocol talked or the URL that we are actually discussing, etc., etc., etc. Okay, so this is the upper layer protocol message, the HTTP payload and the HTTP header, or the DNS payload and the DNS header, etc., etc., etc. And the big idea here is that these two applications, so application A can send this information to application B, and how it actually happens is that the upper layer just prepares this upper layer message and hands it over to the transport layer, so TCP and UDP. If we are talking about HTTP, this will most probably be TCP. The TCP layer takes the upper layer protocol message as an opaque data unit and adds its own metadata to the message. So it basically just precedes the upper layer message with a TCP or a UDP header and adds its own metadata, which is basically will be most probably the ports, or most importantly the ports that identify the applications that talk to each other inside the end hosts, and other important metadata. And when the TCP or UDP stack is ready with the TCP or UDP message, it just hands this message over to the IP layer for sending it over to the other application. So the IP layer again adds a header, the IP header. This is most importantly the source and the IP destination addresses which identify the sender and the destination hosts, which are just participate in this communication session and other metadata, and then it prepares the IP datagram, and again it hands this IP datagram over to the layer 2, the link layer, which will make it possible to send this IP datagram from the first hop router along the internet, which will make sure that the packet will, or this IP datagram will eventually travel to the end host. Now the layer 2 protocol, layer 2 is, or link layer is a little bit special because it not only adds metadata to the head of the packet, so it's not only adds an IP or a layer 2 header, but it's usually it also adds a layer 2 footer as well. So the end of the datagram, but it's basically not that important. Once we have this layer 2 frame ready, the link layer sends it to layer 1, which is basically a physical layer, which converts it into the sequence of zeros and ones, and just sends it over to the transmission medium. And then on the other side, the same flow of operations will be executed in the reverse direction until the original upper layer message will arrive to the upper layer protocol unit. Of course, meanwhile, these different protocol layers will decapsulate the message in the reverse direction as the encapsulation happened on the sender port. Let's quickly jump to TCP/IP principles. TCP/IP, as you can see, is basically the two most important protocols in this protocol stack. Because some of the principles will pretty much transcend all our discussions in the rest of the lectures. So let's just quickly run through these principles. The most important, or at least one of the most important principles here, is the so-called end-to-end principle, which means that per application state only exists at the end host. So intelligence exists at the end, at the edge of the network, at the end host. The network itself is dumb. It does not store microstates, so like it does not store per application state. It basically just does not contain any state at all. The network is dumb, the edge is intelligent, and this makes it possible to scale on the TCP/IP protocol suite from the very little and very small ARPANET experiment 40 years ago to this immense infrastructure that the internet actually is today. The second principle is the connectionless design principle, which in some way can be considered as a consequence of the end-to-end principle. The core scales with the network size and not with the number of end users and applications talking to each other. So if you think about the network size n and the number of applications that might talk at every instance of time to each other, m, then m is usually much larger than n. Any network host can run thousands and thousands of applications. Just think about the web server that at any single instance of time serves thousands of parallel HTTP sessions. The internet core does not store state with respect to each and every application that are talking to each other at any single instance of time, which makes it possible for the internet to scale to the size that we know today. The third principle is the resiliency principle. The internet is supposed to be resilient to large-scale failures. The idea is that this is a code for design which was prepared under nuclear threat. To what extent this was an actual design principle is subject to debates, but rest assured that the internet would be able to survive and it actually is able to survive reasonably huge and large-scale failure events like the Katrina hurricane or similar failure events, This is thanks to the lack of central control. There is no single point of failure in the internet, or at least we are trying to make it so that there is no single point of failure. This is a completely distributed design. There is no internet headquarters where the internet is operated from. The internet is basically just a result of lots of different mechanisms and entities talking to each other and making sure that the internet actually works as we expect it to work. Dynamic routing, the internet can adapt to the changing topology. So whenever a couple of nodes or links go away from the network, the internet can adapt. And the third principle is that packets of a single flow, so any single exchange between two applications, like for instance different packets of a TCP stream, they can travel along different routes through the internet. So this is not fixed, and if there is a failure along the way, the internet will be able to route that around and make sure that your packets will arrive to the destination, as long as there is at least one functional router that will be able to connect you to the destination. The fourth principle is robustness, which is more of a philosophy than an actual principle. This is posed as law on extreme interoperability. Be conservative in what you send, be liberal in what you accept. This basically means that internet protocol and TCP IP protocol implementations most of the time can accept wrongly formatted packets to some extent, or packets which do not perfectly implement the protocol and can try to make best effort, just as an effort to decode the intention of the original sender, which makes it possible for the internet to work even if the actual implementations are not completely interoperable. Short recap on what connectionless and connection-oriented protocols are. Connection-oriented is telephony. So the good idea is telephony, where before the communications we perform a circuit setup, and the actual data units that we send between the senders and the receivers contain the virtual circuit identifier, which is much shorter than the address. So the idea here is that before we make a communication, we actually make a reservation through the rest of the network when we prepare all the state in the network core, and we store the virtual circuits that will identify the packets or the data units of this particular protocol exchange. And the idea is that this virtual circuit identifier is much shorter than the actual addresses of the end host, which makes it possible to implement very fast forwarding. So circuit switching is very fast. We just look up a large hash table and see what's the actual next hop corresponding to the virtual circuit identifier that we find in a packet. The problem is state information. In this case, whenever we store virtual circuit identifier with respect to all pairs of communicating parties and all pairs of communicating applications in the network, the network will scale with big OM, where big OM is, remember, the number of applications talking to each other at any single instance of time, which is much larger than the network size. Okay, now admission control and congestion control is very simple in this case. Connectionless is the complete opposite. This is like the postal service. There is no circuit set up. At any instance of time, you just take an envelope, add the addresses, and drop it into the post box, and it will find somewhat magically the destination address. There is no need to communicate and set up a circuit between the communicating parties. So basically all packets in a connectionless protocol design contain the fully specified destination address and usually the source address as well. The per packet forwarding decision makes it possible that the different packets will arrive to the destination with respect or without respect of the previous packets of the communication session. This is again very similar to the postal service. The nice thing about connectionless is the size of the forwarding tables, which are only which scale with big O n, when n is only the number of hosts and addresses in the network and not the number of applications. So connectionless protocols scale much better than connection-oriented protocols, and this is the big idea in the internet. That's how we could scale the network to the size we know today. Problem is that quite a lot of things are much more complex in connectionless, and as per these complexities, these will be the most important subjects that we will discuss in the rest of this lecture series. Let's just quickly jump to the link layer protocols. Again, we won't really have time to go into the details on Ethernet and the rest of the lower layers protocols. Please make an educated effort to collect and revise all your earlier studies about these layers, because we will assume in the rest of the lecture series that you know the basics about local area networking. So the idea here is that the internet is made up of lots of local area networks. These are LANs or Ethernet clouds, as this is usually just said, or Wi-Fi networks. So all these low-level little networks that make up the internet are connected by routers into a common network infrastructure. There are two very important concepts to know here. A host is a computer on one or more network interfaces endued with a unique IP address. Okay, the IP address is not a link layer concept, but we will need at this point the concept of IP addresses to be able to discuss what's the difference between the link layer and the network layer in the next slide. And the link is a LAN, a local area network infrastructure connecting a subnetwork of hosts. So why we actually just confuse this discussion with the network layer concepts like IP addresses, IP subnetworks, is for you to be able to understand the difference between a switch, a traditional Ethernet switch, and a router, an IP router. Okay, in this little diagram, you see two routers, R1 and R2, and three end hosts, computer 1, computer 2, and computer 3, connected through three switches into an Ethernet local area network. Okay, as you can see, all these IP hosts, C1, C2, C3, R1 and R2, have a different IP address coming from the IP subnetwork 10.0.0.0/24. This is actually IP subnetwork means. We will review it in a couple of slides. It just basically means that this is a collection of IP networks which we assume belong to a single IP subnetwork. Okay, the important thing here is that switches are a purely Ethernet layer concept. They do not process the IP layer of the network protocol stack, or in other words, they do not possess IP addresses. If you just think about an Ethernet switch in this data flow diagram from the earlier slides, you will see that an IP router is basically an entity that processes packets all the way up to the internet layer. Okay, in contrast to an Ethernet switch, which does not process internet layer headers, it just processes the link layer. Okay, as such, switches do not have IP addresses. Of course, there are lots of managed switches, and all new switches can be accessed through IP, but theoretically, the switch does not have an IP address, and as such, the C1 does not have a way to send an IP packet to, say, switch 1. Okay, because there is no IP address to send packets to. The LAN, in other words, the local area network, is completely transparent to the IP host. So R1 will perceive C1 as being connected with a single link. Okay, there is no actual addressable infrastructure between these two end hosts. The link layer, or in other words, the layer 2 is a local area network protocol, Ethernet, PPP, or Wi-Fi. It can be any point-to-point serial link, a long haul, leased line, or anything between. The main idea of the link layer is to transport IP packets between neighboring IP hosts connected to the same subnet. Okay, so this is not, the link layer will not give us access from one host in one continent to another host in another continent, because that's the global internetworking is the responsibility of the internet layer, the IP layer, layer 3. Layer 2 just give us local access or local communication between two hosts on a single IP subnet. The service model is basically everything we will want eventually. So reassembly of IP packets, ordered and reliable transmission, medium access control, error detection, error correction. But remember that these protocols only work between neighboring IP hosts. But the problem is that, of course, not all hosts connected to the internet are connected into a single Ethernet layer, because Ethernet would not scale to those sizes. So the IP layer will basically just repeat all this functionality, but make it possible to connect any two non-neighboring nodes to each other. The most well-known link layer protocol is the Ethernet. This is the .3 protocol used from IEEE. It works from 3 megabits per second all the way to 100 gigabits per second. Now it's also for 4 gigabits per second, and we are slowly approaching terabit per second Ethernet. 48-bit flat address space, and traditionally Ethernet worked with the collision sense multiple access or carrier sense multiple access collision detection medium access protocol. But these days Ethernet is super complex, covering from wire to wireless access, and metro Ethernet and whatnot. Traditionally we used to differentiate between hubs and repeaters to connect different Ethernet segments, which are just dumb Ethernet devices which will blindly repeat all Ethernet frames from one connected segment to the other. Switch is a clever Ethernet device that can know which destination belongs to which segment, for instance using the spanning tree protocol or the shortest path bridging protocol, and then make it sure that only packets or the only destinations or the Ethernet host that belong to a particular segment will get the frames sent there. Here's the Ethernet frame. I won't go into the details on that, but please make sure that you know what the destination MAC address, source MAC address is, what is the ether type, and why do we need the frame checksum.